Welcome all of you. In the last class, we discussed a lot about scalar coupling. Especially, I discussed about the multiplicity pattern. How does the spectrum appear when one proton is coupled to other proton? I showed it is because of the two possible spin states of coupled spin. One proton will become doublet. Similarly, other proton will be seeing the spin states, two spin states of the other coupled proton and become a doublet. When two protons are coupled, I said you will get 4 lines of equal intensity. This is the way we see the coupling, and the total intensity keeps reducing by half each time depending upon the number of protons it is coupled to. When it is coupled to 2 protons, it will become 4 lines and the intensity comes down by 25% each of them. And we worked out and showed that center of the doublet gives a chemical shift and the separation gives you the J coupling if you have 2 coupled spins. Of course, for 3 coupled spins, multiplicity pattern is more and more, then there is a way we can calculate J couplings. And I worked out and showed when there are 2 spin, 3 spin, 4 spins are coupled, the number of transitions or the number of peaks that you are going to get at the site of each spin is given by 2 to the power of n minus 1. And the total number of peaks in the entire spectrum is given by sum of n into 2 to the power of n minus 1. That is what we observed. So, that is what we are going to see, the total number of transitions when we observe a particular spin. So, this we discussed a lot about that, and also we discussed what is called active spin and passive spin. What is active coupling and what is passive coupling? If I have a group of spins, let us say 1, 2 and 3 are coupled. If I am looking at the chemical shift of proton 1, then that is an active spin, and proton 2 and 3 are passive spins. So, 1 can couple to 2 and 3, you get 1 2 and 1 3 coupling at the site of proton 1, and the coupling between 2 and 3 passive coupling you will not see here. Similarly, look at proton 2 or 3, let us say I see proton 3. At the chemical shift of proton 3, you get coupling between 1 and 3 and also 2 and 3. Coupling between 1 and 2 you will not see here because that is a passive coupling. So, we discussed extensively about active coupling and passive coupling and how we can get this information in homonuclear spin coupled spins and heteronuclear coupled spins also. I gave one example each. Then we know how we get the coupling at the site of a particular spin. Then we understood clearly what is active coupling and passive coupling. We will continue further today. Remember in the very first class when I was discussing about the selected features of scalar coupling, I also said the coupling could be positive, negative or 0. That means the coupling has a sign. What do you mean by the sign of the scalar coupling? Whether it is positive or negative, we do not know. How do you get the sign of the coupling? When it is coupling is 0 is very simple. You will get only a single peak, no splitting. But when there is a splitting, I measure the separation, but that does not give me the sign of the coupling. How do I know what is the sign of the coupling? How does the spectrum gets reflected when the sign of the couplings are different? This is what we will try to understand now to go proceed further. For that we follow what is called a Dirac model. If I consider protons, let us say a CH bond, carbon has a nuclear spin and electron surrounded by electron, proton has a nucleus surrounded by electrons and there is a intervening covalent bond. And the most stable orientation of the magnetic moments of proton and electron in a given molecule, consider the carbon atom or a proton hydrogen. The most stable orientation for nuclear spin and the electron spin are when they are anti-parallel to each other. When they are orientation anti-parallel, it is a stable state. This is how it is. Since the electron has a negative magnetic moment, we all know, then the stable state is not parallel orientation but anti-parallel, not anti-parallel orientation, I am sorry, it is a parallel orientation like this. In principle, this is a stable state. If this is proton, this is electron. Since electron is a negative magnetic moment, the stable state is this one. Proton and electron both have the similar orientation, same orientation. The magnetic moment of proton and that of the electron If the alignment is in the same direction, then it is stable state. Okay, this is how it is. To understand the Dirac model, consider the example of one bond coupling between carbon and proton. The nuclear spin has orientation like this. As I said, electron has to be oriented parallel to it to become a stable state, not anti-parallel, because electron has negative magnetic moment I said. Then because electron is oriented like this, in a chemical bond, it ensures that other electron orients opposite to this for its stable state. Of course, you can understand Fermi rule and everything later. And this electron in turn ensure that this is opposite because of stable state, then only it is energetically stable. So, if I have one JCH, only one bond between carbon and proton, then if I start with the proton spin oriented like this, it will ensure such that through the electron other spin oriented opposite to this. That means when this is a lower energy state, when both of them are oriented opposite to each other, it is a stable state. It is a lower energy state. That is a situation where coupling is positive. Coupling is positive means it is stable state, lower energy state. So, that means if I consider one bond carbon and proton coupling, it must be always positive. Because of this Dirac model we can understand. So, one bond this carbon proton coupling is always positive. You may ask me a question, what happens if the proton orientation is like this? There are two possible orientation. I took alpha. What happens if the proton orientation beta is taken? Similarly, this electron will become like this and this electron will become like this and then again this will be like this. So, it is depending upon which orientation of spin you are considering alpha and beta, correspondingly you can work out the orientation of the other coupled spin. If both are anti-parallel to each other, it is a lower energy state and that will be a positive J coupling. So, the sign of the coupling is positive. That is the reason why 1JCH is negative. Then what about two bond couplings of carbon proton and carbon fluorine? I mean carbon proton, 2 bond and 3 bond carbon proton. Again one bond coupling we know, extend it for another bond. It so happens if you extend the same logic, then these two are like this. Higher energy state you will have, that means you are going to get a negative JCH. You go further, it is going to be positive. So, depending upon how the spins are oriented, one bond coupling is 1 JCH is positive, 2 JCH is negative, 3 JCH is positive. You can work it out simply by extending this Dirac model. I worked out only for JCH, but you do not think it will work out for everything. Consider carbon and fluorine one bond carbon fluorine coupling is always negative. You can work out in a different way. Now, if I know the coupling could be positive, negative or 0, how does it get reflected in the NMR spectrum? Let us take the example of two protons coupled and three possible situations when the coupling between them is 0, positive and negative. All the three examples we will take. If I have two protons coupled among them between themselves, as I have been telling you since day 1, there are 4 possible spin states, that is alpha alpha both are up, beta beta both are down, this up and this down, alpha beta, this down this up, it is beta alpha, both are, there are 4 possible spin states we can understand. We will consider a situation coupling between A and X is 0. Of course, we have 4 possible energy states, the energy states are different because the orientations are different. So, beta beta and different magnetic state, different energies. So, now I am writing like this, this is beta beta is -1 total magnetic quantum number and this is 0, alpha alpha is 1. This we knew already, we have discussed how to calculate this one. This is a half total magnetic quantum number for energy state is sum of these two, it will become 1, this is -1 0 0. And I have numbered these energy states as 1 2 3 4 for my case of understanding. So, this is what it is. Let us see now what is going to, how we are going to see the spectrum. The transition between 1 and 3 is allowed. You see -1 to 0 allowed transition. Here which spin is flipping? A is flipping. So, this is A transition. What about this one? Here also A is flipping. 2 to 4 is also allowed transition. This is A transition, this is A transition. What about this one 1 to 2? This is allowed where X spin is changing its orientation from alpha to beta. Similarly, here also 3 to 4 is allowed. Again it is X transition because X spin is changing from alpha to beta and vice versa. But remember, this frequency is same. This energy separation is identical. This energy separation is identical. Look at this energy separation. This is larger, this is smaller. That means this is a higher frequency, this is lower frequency. But these two higher frequency peaks overlap and gives us a single peak. These two will be identical frequency, overlap and gives a single frequency. So that means that we will get two transitions, one for A and one for X. In reality, there are 4 peaks. 2 of A are overlapped, 2 of X are overlapped. 2 transitions each for A and X. When they overlap, it appears as if it is one line. This is the situation when the coupling between A and X is 0. This is a simple example. So when coupling is 0, as this is what we have been discussing. When the coupling is 0, we get only one peak each. Now consider a situation JAX is non-zero, or take it as positive. Whatever it is, non-zero, positive or negative, we will worry later. Now the situation is the total magnetic quantum number of MZ and MX, if they have the same sign like alpha alpha, both are half half, or beta beta, negative minus half, they are called unpaired. Both are like this. Pairing is only when they are opposite to each other. They are unpaired states, unpaired spins. That means their alignment will be less stable. They are not stable because they are unpaired. Pairing means lower energy, unpaired means different. So it is less stable. So these have more energy. These two states will have higher energy. As a consequence, what will happen? Alpha alpha and beta beta state, because of their unpaired spins, their energy level gets destabilized and pushes up. How much it is pushed up, the energy state? By what is called J by 4. I will show you dry by picture. Please remember, when we consider the alpha alpha and beta beta states, the energy states are pushed up by, this is the energy state, it pushes up by J by 4, and this will be energy state now. Similarly, if it is beta beta, it pushed up by J by 4. This is the situation we are going to get for the unpaired states, unpaired spin. Now we consider situation where it is paired, alpha beta and beta alpha, they are paired spins. Their alignment will be more stable, so they have less energy. Then obviously, if you consider the states alpha beta and beta alpha, they get stabilized and then energy comes down, they push down, their energy is decreased by J by 4. So if this is the state for alpha beta or beta alpha, instead of going up, it comes down by J by 4. In other case, this is alpha alpha and beta beta, this went up by J by 4. So that is how the energy states get destabilized. In the earlier case, here it is stabilized. When it is stabilized, comes down by J by 4. When it is destabilized, it goes up by J by 4. And now let us see the energy level diagram. Consider the situation JAX is 0, we already know this. As I said, JAX is positive, greater than 0, then what is going to happen is, just now I explained to you, beta beta states are pushed up by J by 4. Similarly, alpha alpha state is pushed up by J by 4. Beta alpha states come down by J by 4. This also comes down by J by 4. There is a shifting. Energy states are stabilized and destabilized because of pairing and unpairing of the nuclear spins. Now let us calculate the frequency of the transitions. Again, 1, 2, 3, 4 if I write, 1, 2, 3, 4 energy states. 1 to 3 is allowed, that is A transition. This is also allowed, 2 to 4, and this is allowed, 1 to 2, that is X, and this is X. Well, now what is happening? This has a more energy, higher frequency. This is compared to this is less energy, lower frequency. So we have 2 lines, one at higher frequency, other at lower frequency. Similarly, X has higher frequency and lower frequency. There are 2 peaks. So this is what we saw. When the 2 spins are coupled, we get 2 lines each. And now you can see the frequency of one of them is larger than the other one. That's why one moves to higher frequency, other moves to lower frequency. Exactly here for the X also. So that's how we can understand, because of 4 energy states, when there is a coupling, there is stabilization and destabilization of paired and unpaired states as a consequence of this one. So, that is how we get 4 transitions, and I told you transition 1 to 3 is A, 2 to 4 is A, transition 1 to 2 is X, 3 to 4 is X. And this is the 4 lines pattern you expect when the JIX is 0, greater than 0. This is separation gives you coupling, this gives you center of them chemical shifts of A and X. This is an example of the spectrum for 2 coupled spins A and X. Let us go further. This is what we understood for AX positive, J coupling positive. We will go to a situation, this is what we understood. What will happen to the energy states when the coupling is negative? Reverse will happen. What will happen? When the coupling is negative, the unpaired states gets destabilized, unpaired state gets stabilized and paired state gets destabilized because the coupling is negative. This is what happens. Now, beta beta comes down and beta alpha goes up. Exactly here alpha beta goes up and alpha alpha comes down. Here what happened, you see, beta beta and alpha alpha both were going up and these two are coming down. Here these two are going up and these two are coming down because the coupling is negative. Everything gets reversed. Let us see the transitions now. This is 1 3 transitions. If I take 1 2 3 4 are the 4 energy states, that is for A, and this is again A transition. See the difference now. What did you observe? Higher energy, the energy separation larger, higher frequency. Higher frequency was this, now higher frequency became, higher frequency was between 1 and 3, now it became 2 and 4. See the difference. And lower frequency was 2 and 4, now lower frequency became 1 and 3. The lines got interchanged. Higher frequency and lower frequency transitions get interchanged for A. Exactly. For X spin also, this is 1 2 transition and this is 3 4. See, earlier 1 2 was larger frequency, larger energy separation, and 3 4 was smaller, but now 1 2 is smaller and 3 4 is larger. What did you understand? The transition in the previous case I showed you here in the previous slide, this is for 1 3, this is for 2 4, this is for higher frequency, this is for lower frequency. Energy from the energy separation I can say that. For A, this is again higher frequency and lower frequency for X. But what happened in this case is everything get reversed. So, when the coupling is negative, the larger separation, that higher frequency and the lower separation are now interchanged. As a consequence, the frequency of the two transitions get interchanged. What happens? The appearance of the spectrum, and this was earlier 1 3 and this was 2 4. Now, you see this became 2 4, this became 1 and 3 transition. Earlier this was 1 and 2, now it became 3 and 4, and earlier this was 3 4 transition, now it become 1 2 transition. What happened? The peaks from here to here got interchanged. Just let us look at the color here. In the color spectrum, I wrote here some color. You see, these were, let us say magenta color was the left higher frequency and the other one was green color was the lower frequency in both the cases. But in this case again what happens? You see, magenta became lower frequency, green became higher frequency. Exactly here also. The lines got reversed, interchanged. Transition from 1 2 became 3 4, 3 4 became 1 2, similarly 2 4 became 1 3, 1 3 became 2 4. This is exactly what happened. So, can you see the difference if I do not tell you this? If I do not tell you, if I give you only the spectrum of 2 lines, you will not know whether it is positive or negative. What does it mean? The splitting pattern are independent of the signs of the coupling constant. So, that means one dimensional NMR spectrum does not give sign of the couplings. So, if I give you the NMR spectrum, you will not, I will measure the coupling, but you will not say, you cannot say whether it is positive or negative, because the spectrum remains invariant with the change in the sign of the couplings. This is what I wanted to tell you. So, I hope you understood about the sign of the coupling, how the sign of the coupling matters in the spectrum. It matters in the stabilization and destabilization of the energy levels, but as far the real spectrum is concerned, you will not see the difference, you will not see the effect of it at all. Alright, hope it is clear for you. With this, I will introduce one more term which is essential for observing the NMR spectrum and multiplicity of the NMR spectrum. that is called magnetic equivalence. We will discuss what is magnetic equivalence. Remember, I told you chemical equivalence earlier before discussing the J coupling. I said in the chemical equivalence there is a symmetry operation. Symmetry operation ensure that the particular protons will have identical chemical environment and they give rise to a single peak. There is no separation, they come at the same chemical shift. But I did not say about the coupling, there could be coupling between them. Okay, there may not be coupling, there may be coupling also, both are possible. And when we bring into the coupling, in addition to chemical equivalence, we introduced another term called magnetic equivalence. That is what I am going to introduce now. Look at it, magnetically equivalent nuclei means not only they have the same chemical shifts and they should have identical scalar coupling to all other coupled spins. Very interesting. Remember, not only chemical shift should be same, the coupling strength to the remaining coupled protons to which it is coupled to are all identical. They should not be different. I will show you that with an example. For example, I have 3 protons. When they say all the 3 protons are magnetically equivalent in a molecule, what does it mean? The chemical shift of 1, delta of 1, chemical shift of 2, delta 2 and delta 3 or chemical shift of 3, all the 3 should be identical. That means they should be chemically equivalent. In addition to that, there may be a coupling. J12 is there, coupling between 1 and 2, coupling between 2 and 3 is there, and coupling between 1 and 3 are also there. All the 3 are there. So, that means all the 3 couplings are should be equal. Not only they are present, they should be equal. Not only chemical should be identical, even coupling should be identical. Then these 3 protons 1, 2 and 3 are called magnetically equivalent spins. You understood? Magnetically equivalent spins. Now you can understand the statement. All magnetically equivalent nuclei are invariably chemically equivalent because of the chemical shift being identical only we discussed, and at the same time we have brought in another condition, J coupling being identical. So, that means all magnetically equivalent nuclei must be invariably chemically equivalent. But what about the reverse? Converse is not true. All chemically equivalent spins need not be magnetically equivalent because coupling can be different. Okay, only when the couplings are same they are magnetically equivalent. So, this is the important point. Please remember, I stress it again, all magnetically equivalent spins are chemically equivalent, but all chemically equivalent spins are not magnetically equivalent. Let us look at the example here. I am taking the example of one molecule. Is there a symmetry axis for this? Of course, there is a symmetry axis here. When there is a, because of that, this proton and this proton are chemically equivalent. Chemical shift is same. Nu 1 is equal to or delta 1 equal to delta 2. Chemical shift are same. They are chemically equivalent. Now, the fluorine is there. There can be a coupling between 1 and photon and fluorine 1 and 3. There can be a coupling between 2 and 3. It is possible. In which case J13 is also equal to J23 in this molecule because it is a perfect symmetry. 1,3 coupling is also equal to 2,3. Not only chemical shifts are same, delta 1 equal to delta 2, J coupling J13 is also equal to J23. That means 2 protons are magnetically equivalent. It satisfies the condition. Not only the chemical shifts are there, not only they are chemically equivalent, they are also magnetically equivalent because the couplings are same. So, this is the condition for magnetic equivalence. This is one example. We can take the example of this molecule. What is this molecule? There is a symmetry. There are 2 CH3. So, this CH3 chemical shift and this CH3 chemical shifts are same. They are chemically equivalent. But what about the coupling between this proton and this CH3 and this proton and this CH3? What is the coupling between 1,3 and 2,3? J13 is again equal to J23. That means these 2 methyl protons are magnetically equivalent. Okay. Consider this classic example of methane. This methane has 4 protons. Very interestingly, all the 4 protons 1, 2, 3 and 4 they are chemically equivalent, they come at the same chemical shift. Whatever the coupling, there are several couplings, 1,2 coupling, 1,3, 1,4, 2,3, 2,4, 3,4, all couplings are present, but all of them are equal, identical coupling. So, the methane is a classic example of all the 4 protons which are magnetically equivalent. Okay, this is an example, all the 6 couplings are same, all the 4 chemical shifts are same. But we can come across some funny situations also. We can come across magnetic equivalence with multiple couplings. Look at this molecule. This is 1,4 difluoro, I mean 2 chlorobenzene, whatever that name. We have 2 protons and 2 fluorines. Consider the chemical shift of fluorine, 1 and 4 are same. Consider the chemical shift of protons, 2 and 3 are same. What is the coupling 1, 2? Is equal to 3, 4. What is the coupling 1, 3? Is equal to 2, 4. That means each proton experiences 2 coupling, 1, 2 and 2, 4. This proton 3, 4 and 1, 3. Each proton experiences 2 couplings. Similarly, each fluorine experiences 2 couplings. This fluorine experiences 2 couplings. That means each fluorine, and the interesting thing is 3, 4 is not equal to 2, 4. 3, 4 is not equal to 2, 4, they are different. But each proton experiences 2 different couplings, each fluorine experiences 2 different couplings. That means 2 protons are magnetically equivalent and 2 fluorines are also magnetically equivalent. Go to the example of benzene. We all know benzene has 6 protons. Let us look at 6 protons, all the 6 protons of benzene come at the same chemical shift, all of them have the same frequency, resulting frequency, all are equal. At the same time, each proton can experience 3 different couplings. Consider this proton 1, it can have an ortho coupling, it can have a meta coupling and it can have a para coupling. Each proton experiences 3 different types of couplings, but couplings are identical. For example, this is what we said for proton 1. Go to the proton 2, this has ortho coupling, this has meta coupling, this has para coupling. So, each proton experiences 3 different couplings of identical strengths, because this ortho, meta, para couplings are not identical in benzene. Ortho coupling is 8.5 hertz, meta is 1.5, para is 0.5 approximately, they are different strengths. So, but nevertheless it gives a single peak in the NMR. That means all protons are chemically equivalent. At the same time, in spite of multiplicity of the couplings, multiple couplings present, all protons experiences the same type of couplings. So, it is magnetically equivalent spin with multiple couplings. This is another example, ethylene. Ethylene, all the 4 protons are chemically equivalent, but 1, 2 is the coupling is different from 1, 3, different from 2, 4 or 1, 4. Similarly, consider 2, this coupling and this coupling are different. Consider this and these couplings are different. So, all this example I am giving you, ethylene also is a classic example of magnetically equivalent spins with 3 different couplings. Benzene is also example of magnetically equivalent spin with 3 different couplings. So, these are all examples of classical example of chemically and magnetically equivalent spins with multiple couplings. Not only there are multiple couplings, sometimes there can be single coupling also, but magnetically equivalent, important point you should remember is all magnetically equivalent spins are chemically equivalent and the converse is not true. And all these magnetically equivalent spins, if you take the NMR spectrum, they give rise to a single peak. For example, this ethylene gives rise to a single peak in NMR. Similarly, benzene gives rise to a single peak in NMR, although there are 3 couplings. Methane, there are different couplings, 5 or 6 couplings are there, but all of them are identical. All proton chemical shifts are identical and gives a single peak in NMR. So, this is the concept of magnetically equivalence. So, since the time is getting up, I am going to stop here, but what we discussed today, I would just like to summarize in couple of sentences. See, we started discussing about the multiplicity pattern yesterday, and today we wanted to talk about relative signs of the coupling. As I said, the coupling could be positive, negative or 0. How does this sign of the coupling is getting reflected in the NMR spectrum? When the coupling is 0, we took the example of 2 coupled spins, 4 possible energy states. In the 4 possible energy state, beta beta, alpha alpha, alpha beta beta alpha, there are 4 possible transitions, 2 for A, 2 for X. 2 A transitions will overlap, 2 X transitions will overlap and gives us to only 2 peaks. Chemical shifts are different. That is when the coupling is 0. I said when the coupling is present, not only present, if it is positive, what will happen? Alpha alpha and beta beta are unpaired spins. Their energy states get destabilized. As a consequence, they are pushed up by J by 4. So, energy gets changed by J by 4. Whereas alpha beta and beta alpha states are paired spins. Their energy states are pushed down by J by 4. Now, we calculate the frequencies. Again, transitions which are allowed for A transitions and X transition we found out. One of the A transition has higher frequency and the other one has lower frequency. So, that is how we get a doublet when there is a coupling. Similarly, X has one higher frequency, X has one lower frequency. So, they are all again 2 lines for A and 2 lines for X, and this separation gave me JAX, but I do not know positive or negative. But I know AX coupling give 4 peaks, 2 spins are coupled, we get 4 peaks. That is fine. We also understood what happens if the coupling is negative. Then reverse will happen. Alpha alpha states, instead of pushing up, they get stabilized, comes down. Similarly, beta beta comes down, whereas alpha beta beta alpha state pushes up. The states gets reversed. Calculate the energies, calculate the frequency again. Now, same 1,3 transition which was higher frequency now became lower, and 2,4 transition which was lower frequency became higher because of large energy separation. So, same thing is true with X spin. So, that means the 2 lines which were like this get reversed like this. It was like this, became like this. So, one dimensional NMR spectrum if you take, you will not know the effect of coupling at all. The appearance of the spectrum remains invariant. It remains invariant with the change in the sign of the coupling. This is what we understood. And also I introduced about magnetic equivalence. Magnetic equivalence is the situation where not only spin should be chemically equivalent, that means chemical should be same. Each spin which it should be having a same identical coupling strength with other protons which it is coupled to. I took the example of methane. One proton is coupled to remaining 3 protons of the same coupling strength. All the 4 protons of the methane have the same chemical shift. So, it is a perfect example of magnetic equivalence. Another example is benzene and ethylene we took. Each of them have multiple couplings. Benzene has 3 couplings, again ethylene has 3 different couplings. But each of the protons of benzene has 3 couplings, identical 3 couplings. Coupling strengths are same. Each of them experience ortho meta para couplings. Similarly, ethylene, each proton experiences 3 couplings of identical strengths. These are also example of magnetic equivalence with multiple couplings. This is what we discussed today, and further lot more we have to understand about the interpretation of the NMR spectrum. We will continue with that in the next class. I am going to stop it here. Thank you very much.